The first functional group which we are going to learn today is alcohol functional group. Alcohols are a class of compounds that contain an OH functional group. OH functional group is also referred to as hydroxyl group. In alcohols, the oxygen is bonded to a tetrahedral carbon as shown in this bond and stick model. The red sphere represents the oxygen atom. So this would be the OH. So oxygen would be the red sphere and hydrogen would be the white sphere. And this black sphere is the carbon atom. And as you can see, the carbon atom is a tetrahedral uh, atom. So oxygen is bonded to the carbon, and this carbon is tetrahedral. The Lewis structure of this alcohol molecule is shown here. The name of this alcohol is methanol. Another example of an alcohol where OH group is bonded to a 2-carbon atom chain. So in this case, the name of this alcohol is ethanol. Ethanol is also known as drinking alcohol, and it is present in wines and whiskey and beer and all alcoholic beverages. So ethanol is the alcohol which is present in all alcoholic beverages. Another common example of alcohol is 2-propanol. It is also known as isopropyl alcohol. We also know this alcohol by the name of rubbing alcohol or IPA. So this is the one which we use to disinfect any cuts and wounds on our skin. In this case, the OH group is again connected to the tetrahedral carbon atom. So in general, in alcohols, the OH group will be connected to a carbon atom which may be a part of a longer carbon chain. So as you can see in all these different alcohols, we do have a OH or hydroxyl group linked to a carbon atom, and that carbon atom may be a part of a longer chain. So in general, we denote these carbon chains by R. So R and then OH. So R would mean some carbon chain. It could be a 1-carbon chain as in case of methanol, or it could be 2 or 3-carbon chain. And OH group refers to a alcohol functional group. So the general formula by which we represent alcohol is ROH, where R represents some carbon chain and OH is the hydroxyl group, which is the functional group for alcohols. Another thing to notice here is that the geometry around the OH group is a bent. So as you can see, this is a bent geometry just like the one we find in water molecule. The angle here is also 109.5 degrees. So all alcohol molecules, or functional groups, they have bent geometry. Let's write the skeletal line structures and condensed notation for these alcohols. For A, so let's first write the skeletal line structure. So in this, if we count, we do have a 1, 2, 3, 4, and 5 carbon chain, and then the alcohol functional group. So as we know, in skeletal line structure, we represent the carbon chain with a zigzag line. So that would be 1, 2, 3, 4, and 5 carbons, and then we have a alcohol functional group, and we do show the hydrogen connected to the heteroatom. So this would be the line structure, and the condensed notation for this would be, in condensed notation we do not show the bonds, but we do show all carbons and hydrogen. So this would be CH3, CH2, 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 and OH. In case of molecule shown in example B, so here again we do have a 5-carbon chain, as shown here, but the alcohol functional group is connected to the middle carbon. So again, we will show the carbon chain with a zigzag line. So that would starting from here. So 1, 2, and that's the number 3 carbon. 1, 2, 3, 4, and 5. So that would be 4 and 5. And then on number 3 carbon, we have a alcohol functional group. And this is the line structure. And let's write the condensed structure. So starting from carbon 1, so that would be CH3. So that's carbon 1. So carbon 2 is CH2. And carbon 3 is, there is only one hydrogen connected to carbon 3, but it does have OH. So because it's in the middle of the molecule and OH is kind of like a side chain, so we show this in parentheses. That's one way of showing it. I'll show the other way. So that, let's continue with carbon number 4. That's carbon 3 and then CH3. Another way you can show the condensed structure is CH3, CH2, and then CH, and then just show that OH is connected to carbon number 3. This is the easier way, so less confusing. So I would recommend you to use this condensed notation. The IUPAC rules for naming alcohols are based on the rules for naming alkanes as described in previous chapter. There are some modifications and few additional rules while naming alcohols. These modifications and additional rules are described in this slide. The first modification is that while identifying the longest chain, we must make sure that the hydroxyl group or the OH group is present on that longest chain. For example, a Lewis structure of one of the alcohol is shown here. So in this case, our longest chain is the horizontal chain. As we can see that in this longest chain, the alcohol or hydroxyl group is indeed connected to one of the carbon atom. The second rule is we assign the parent name and replace the E at the end of the name with OL. So in the example shown, the longest chain is 6 carbon long, and also we make sure that the numbering is done from the side which gives the hydroxyl group the lowest number. So we will come back to that rule in a little while. So first, let's pay attention to the length of this chain. So the length of this chain is 6 carbon long, and from the rules as we learned in case of alkanes, the name of alkane with 6 carbon long chain is hexane. So in case of alcohols, we replace the E at the end. So this E is removed and instead we add OL at the end. So the name of this alcohol will become hexane. We're gonna remove the E and we will add OL. So the name of this alcohol is hexanol. So E is replaced and we add OL. After we figure out the name of our alcohol, now we need to identify the locator number or at what carbon the hydroxyl group is connected. So in order to do that, we need to number the parent chain. We start from the end which is closer to the hydroxyl group. In the example shown in this slide, the hydroxyl group is closer to the right hand side, so therefore we will number from the right hand side. So this would be number 1 carbon, number 2, 3, 4, 5, and 6. So while we number it, we can see that the hydroxyl group is connected to number 2 carbon. So therefore the locator number for hydroxyl group is number 2. And finally, we place the locator number at the beginning of the name, uh, and we place a hyphen between the locator number and the name. So this locator number identifies the position of OH group on the carbon chain. So in this case, the OH group is located at number 2 carbon. So therefore, we will put number 2 and a hyphen. So the complete name of this alcohol is 2-hexanol. In case of branch chain alcohols, we apply the rules for branch chain alkanes learned in previous chapter using the numbering of the parent chain as described in previous slide. For example, a branch chain alcohol is shown in this picture. So let's try to assign the name to this branch chain alcohol. So first rule which we learned in previous slide was to identify the longest chain. So let's identify the longest chain, and while doing that, we need to make sure that the OH group is present on the longest chain. So in this case, again, our longest chain is the horizontal chain, and it is consists of 6 carbon, and also the OH group is connected to this longest chain. Now, apart from OH group, we will identify any branched alkyl groups connected to this longest chain, and if we look carefully, we can see that one of the methyl group is also connected to this longest parent chain. After we identify the longest chain, now we are ready to give the name of this parent alcohol. So the parent alcohol would again be hexanol because it has 6 carbon chain. Now we need to identify the locator numbers. Again, as we learned in the previous slide, the numbering of parent chain is done from that side where the OH group is closer to. So in this case, again, the OH group is closer to the right hand side, so therefore we will number from the right hand side. So this will be carbon 1, 2, 3, 4, 5, and 6. So OH group is connected to number 2 carbon, and our methyl group is connected to number 5 carbon. So now we know the locator number. Let's assemble the name together. So first we write the alkyl chain substituent, so which is a methyl group. So this group is a methyl group, and this methyl group is connected to it's connected to number 4 carbon. So therefore the name of this whole branch chain alcohol will start with 4-methyl. There is no other alkyl substituent, so rest of the name will be the name of alcohol. So hyphen 2-hexanol. So this is the complete name for this branched chain alcohol. After learning how to name any alcohol, if the structure is given, we should also be able to do the opposite. That is, in case the name is provided, we should be able to write or draw the structure of that alcohol. Let's take a look at a few examples. In these problems, the names of 3 different alcohols are given to us, and we need to write their structures. So let's start with the first one. So the name of this alcohol is 3-octanol. So first we need to look at the parent chain of this alcohol, or parent carbon chain of this alcohol. That comes from the first word, oct. Oct means 8. So that means that our alcohol has 8 carbon atoms in the main chain, or main parent chain of that alcohol. So let's draw the carbon chain with 8 carbons. Because we are writing the skeletal line structure, so I will use a zigzag lines to show the length of our parent chain. So that would be so 1, 2, 3, 4, 5, 6, 7, and 8. So that's my main carbon chain present in the alcohol. So now because it's an alcohol, so it must contain the hydroxyl group. And at what position hydroxyl group is present? So it says 3 octanol. That means hydroxyl group is present at number 3 carbon within the chain. So let's number it. So at this point, it doesn't matter whether you number from left side or right side. So it's 1, 2, and 3, 4, 5, 6, 7, and 8. Because alcohol group is present at number 3, so I'm going to draw the OH group at number 3. So this is the structure of 3-octanol. Next is cyclopentanol. So cyclopentanol means it's an alcohol with cyclopentane. So cyclopentane is a cyclic hydrocarbon with a pentagon kind of structure, and because it's an alcohol, because it must contain an OH group, so in this case you can attach OH group on any carbon. It could be this way or it could be this way. It does not matter where you draw the OH group, it's always gonna be cyclopentanol. And finally, last example is 5,6 dimethyl. So that means that we have now a branched alcohol with two methyl groups connected at number 5 position and number 6 position. So let's try to identify the main chain length, which is heptane or heptanol. So therefore the main chain is heptane, or 7 carbons. So let's draw the main chain first. So that's 1, 2, 3, 4, 5, 6, and 7. Let's number it. That's number 1, number 2, number 3, 4, 5, 6, and 7. It says 1 heptanol. That means the OH group is at number 1 position. So let's connect the OH group at number 1. And now it says 5,6 dimethyl. It means at number 5 and number 6 we have methyl groups are connected. So therefore number 5 has a methyl and number 6 has a methyl. And this is the structure. The chemical reactivity of an alcohol depends on the number of other carbon atoms connected to the one which is linked to the OH group. For example, in case of an alcohol where the carbon atom which is connected to the OH group, as highlighted in yellow color, is linked to only one more carbon atom. For example, in this case, the carbon atom which is linked to the OH group is connected to only one more carbon atom. So these kind of alcohols are categorized as primary alcohol. And primary alcohols are denoted by this symbol, one with a knot. So primary alcohols are those alcohols where the carbon atoms linked to the hydroxyl group is connected to only one more carbon atom. Depending on this, alcohols are categorized in 3 categories. So primary alcohols, we have already defined what are primary alcohols. Another example of primary alcohol is also shown here. As we can see that the carbon atom which is linked to the OH group is connected to only one more R. R group represents an alkyl chain or another carbon chain. So therefore this would be a primary alcohol. Secondary alcohol are those alcohols in which the carbon atom connected to the hydroxyl group is linked to 2 more carbon chains or carbon atoms. So as we can see here, in this case, the carbon atom containing the hydroxyl group is linked to two more carbon chains or carbon atoms. And similarly, the tertiary alcohols are those alcohols in which the carbon atom containing the hydroxyl group is linked to three more carbon chains or carbon atoms. Let's write another example. So if we have an alcohol as shown here, in this case, the carbon atom which is connected to the hydroxyl group is this one. So let's number it number one carbon atom. So this number one carbon atom is linked to another carbon atom at number two position, and it also contains a branch group. So this one, that's also a carbon atom. So as number one carbon atom contains the OH, and it is also connected to two more carbon atoms, therefore this alcohol is a secondary alcohol. So that's how we identify if an alcohol is primary, secondary, or tertiary. Let's identify if these examples of alcohols fall under the category of primary, secondary, or tertiary alcohols. So let's take a look at first example. So in this case, the carbon atom which contains the OH group, so that's the number two carbon atom from the right. So now we need to look at this carbon connected to how many more carbons. So this carbon is connected to one more on the right hand side and another one on the left hand side. So therefore the carbon atom containing the hydroxyl group is linked to two more carbons, so one here and one here. So therefore this alcohol is a secondary alcohol. In example B, the carbon atom which contains the hydroxyl group, that would be the carbon shown here, and this carbon is linked to only one more carbon at this position, so therefore this alcohol is primary alcohol. In example C, the carbon containing the hydroxyl group is in the middle, and this middle carbon is connected to one on the left hand side and the other carbon on the right hand side, so it's linked to these two carbon atoms. So therefore this alcohol is a secondary alcohol. And finally, the last example, the carbon containing the hydroxyl group is in the middle, and this carbon is connected to one atom here, another carbon atom here, and another carbon atom here. So it's connected to three more carbon atoms. So therefore this alcohol is a tertiary alcohol. Alcohols containing two hydroxyl groups are known as diols, and alcohols containing three hydroxyl groups are known as triols. And if we have an alcohol which contains multiple hydroxyl groups, that is more than three, those alcohols are known as polyols. Poly means many, ol means alcohol. Similarly, di means two, and ol is a suffix we use for alcohol. So diol means an alcohol containing two OH groups. The examples of these different kind of alcohols with multiple OH groups are shown here. In first example, this alcohol contains two hydroxyl groups, so therefore this is an example of diol. So its name is ethylene glycol. In the second example, again, this alcohol contains two OH groups, so it's also a diol, and the name for this diol is propylene glycol. And finally, in the third example, we have an alcohol with three hydroxyl groups. Therefore, this is an example of triol. Triols are also shown in this skeletal structural form, and the name for this triol is glycerol. Remember, diol, triol, and polyols are categories, and we may have multiple alcohols which fit in these categories. Ethylene glycol and propylene glycols are commonly found in antifreeze solutions. Glycerol is an important triol which is produced during the metabolism uh, of glucose and fats. Glucose is an example of a polyol. We will learn more about glucose in carbohydrate chapter, but glucose molecule contains multiple OH groups, so therefore it falls under the category of polyols. As we can see in this structure of glucose molecule that it contains multiple hydroxyl groups, so therefore it falls under the category of polyols. So glucose is a monosaccharide, which is a simple sugar, and it is a carbohydrate, and we will learn more about carbohydrates in chapter number 14. Let's solve this alcohol related problem. In this problem, the structure of Latanoprost, which is used to treat glaucoma, is shown here. So first we need to identify and circle the alcohol functional groups. So remember, alcohol functional group is a OH functional group, and let's circle these functional groups. In the second part, we need to label the hydroxyl groups as primary, secondary, or tertiary. Primary or secondary tertiary can be identified by looking at the carbon atoms where the hydroxyl group is connected to, and we need to see how many more carbon atoms that particular carbon atom is connected to. So for example, in here, this carbon atom is linked to 2 more carbon atoms. So therefore, this alcohol group would be a secondary alcohol group. Similarly, the OH group in the middle is linked to a carbon atom which is further linked to 2 more carbon atoms. Therefore, this would also be a secondary alcohol group. And finally, the third hydroxyl group is linked to a carbon atom which is also connected to 2 more carbon atoms on both sides. So therefore, this is also secondary. So all of these hydroxyl groups are secondary. Finally, we need to answer if Latanoprost is a diol, triol, or polyol. Because it contains 3 OH group, therefore it is a triol. Solubility depends on the polarity of a solute and solvent. Previously, we learned about a general concept of like dissolves like. The meaning of this concept is that polar solutes will dissolve in polar solvents such as water. On the other hand, non-polar solutes or non-polar compounds will dissolve in non-polar solvents. Hydroxyl group is one of the very polar group, and it is capable of forming hydrogen bonding. As we saw in case of water, which contains OH groups, and water OH groups form hydrogen bonds with other water molecules, and hence any other compound which does contain OH group will be capable of forming hydrogen bonding with water and hence will be soluble in water. So therefore we can say that alcohols, because they do contain hydroxyl group, should be able to dissolve in water because they do contain OH group. On the other hand, any compound which contains carbon-carbon chains such as hydrocarbons or alkanes, alkenes and alkynes, they are non-polar and hence all of these nonpolar compounds should be soluble in nonpolar solvents. Alcohols, it turns out, also contain carbon-carbon and carbon-hydrogen bonds, and all these bonds are nonpolar. So now we should assume that alcohols should be able to dissolve in nonpolar solvent. But what really it is, are they soluble in polar or nonpolar? The answer to this question depends on the length of the carbon-carbon chain as well as the number of hydroxyl groups present in the alcohol molecules. If alcohols contain relatively small number of carbon atoms such as 1 carbon or 2 or 3, so in that case the non-polar part is small enough and the polar part or the hydroxyl group is strong enough, so these alcohols, because of a relatively small number of non-polar carbon hydrogen units, should be soluble in water. In case if we have alcohols which have significantly large number of carbon-carbon atoms and carbon-hydrogen atoms, then these alcohols should be insoluble. So any alcohol with the carbon chain more than 5 carbons, as shown here, they have significantly large amount of non-polar part, hence they all will be insoluble in water. The butanol or alcohol with only 4 carbon chains, it's somewhere in the middle, so this is partially soluble in water. In this case the non-polar carbon chain is moderately high enough, but hydroxyl group is also there, so therefore uh, uh, alcohol with 4 carbon chain is partially soluble in water. The solubility of alcohol is also greatly affected by the number of hydroxyl groups. For example, in case of glucose, it contains multiple hydroxyl groups. Although it does contain significantly large number of carbon atoms, 6 carbon atoms to be exact. Uh, However, the number of hydroxyl groups is high enough, therefore glucose is highly soluble in water. On the other hand, cholesterol contains very large number of carbon atoms but only one hydroxyl group. In that case, this one hydroxyl group is too small to um, make this molecule polar enough to be soluble in water. Hence, cholesterol is insoluble in water and it is highly soluble in non-polar solvents. Because of these solubility differences, uh, glucose dissolves readily in blood. Blood is also polar, water-based, and it can be transferred or transported in all parts of body with the help of blood. Whereas cholesterol, being insoluble in water, uh, therefore, it is transported through the circulatory system in a special molecule assemblies which are known as lipoprotein complexes. We will learn more about these lipoprotein complexes in chapter number 15. The capability of alcohols to form hydrogen bonds, as shown here, also accounts for their higher boiling points compared to other organic molecules with similar size. For example, methanol, ethanol, and 2-propanol are liquid at room temperature, whereas alkanes of similar size, that is methane, ethane, and propane, are all gases. Which of these compounds have a higher boiling point, hexane or 1-pentanol? The answer is 1-pentanol will have a higher boiling point. The reason is because of the presence of hydroxyl group, which is polar in nature. One pentanol, like all other alcohols, is capable of forming hydrogen bonds with other alcohol molecules because of the presence of uh, strong intermolecular forces, that is the hydrogen bonds. Uh, we will need more energy to convert the liquid state alcohol to gas state, and hence one pentanol will have a higher boiling point. No such hydrogen bonds are present in hexane, so therefore uh, boiling of hexane is easy because various hexane molecules are held together by weak London dispersion forces, and these weak London dispersion forces need very little energy to break, and hence boiling of hexane is easier as compared to 1-pentanol. In previous chapter, we learned about aromatic hydrocarbons. Aromatic hydrocarbons are those organic compounds which contain an aromatic ring known as benzene ring, as shown here. Benzene ring has a 6-carbon ring structure with alternating double and single bonds, and all of these carbons are connected with one hydrogen atom. An aromatic ring that has one of the hydrogen atoms replaced with hydroxyl group is known as a phenol. So this is classified as a phenol. The ball and stick model for phenol is shown here, and the skeletal line structures of phenols are also shown down here. It should be noted that aromatic ring and the hydroxyl group act as a one unit. So this entire phenol is a single unit, which is different from alcohols. In alcohols, the only hydroxyl group is the functional group, but in case of phenol, the entire aromatic ring and the OH group are together classified as a phenol functional group. In previous chapter, we also learned that there are several ways to write the aromatic ring. Because of the delocalization of these double bonds, they could be shown this way, or they can also be shown as a circular ring in the middle. So therefore, phenol can also be shown by any of these three skeletal line structures. Phenols are found in many compounds present in nature as well as in industry. For example, vanillin, the substance that gives vanilla its flavor, and eugenol, the fragrant substance in cloves, are examples of molecules which contain phenol functional groups. So the structure of eugenol from cloves is shown here, and the structure of vanillin, which is present in vanilla bean, and this compound gives the typical vanilla flavor, also contains the phenol functional group. The simplest molecule which contains the phenol functional group is shown here, and this compound was one of the first compound used as an antiseptic. A 5% aqueous solution of phenol destroys the dangerous anthrax bacterium in 48 hours. Many other disinfectants contain a phenol functional groups, and they are used to kill germs. Phenol functional group is also found in many antioxidant substances such as vitamin E, as shown here. An antioxidant is a compound that captures free radicals, including the damaging free radicals produced in a cell. Free radicals are very reactive atoms and molecules characterized by an unpaired single non-bonding electron. Research has shown that free radicals initiate the disease processes and play a important role in aging process. Phenols are named similarly to aromatic hydrocarbons, which we learned in previous chapter. In case of phenol nomenclature, we use the parent name phenol instead of benzene, which was used in aromatic hydrocarbons. Also, there is another modification that in case of phenols, carbon bonded to hydroxyl group is always considered as carbon number 1. For example, if we have a phenol with the additional substituent, so when we name this phenol, we always give carbon where OH group is connected as carbon number 1, and then the other numbering is given according to the rules learned in nomenclature of aromatic compounds. So therefore, in this case, because we have ethyl functional group at this position, and we have a methyl functional group at the bottom part of our phenol, so therefore we will number it anti-clockwise direction, and this carbon will be number 2, number 3, number 4, number 5, and number 6. So therefore name of this phenol will be, first we write the names of alkyl substituent alphabetically. So ethyl comes first, it will be 3-ethyl, 5-methyl, and there is no need to write one phenol because it's understood that the OH group is always number 1, so we don't need to write the locator number for OH group or hydroxyl group, so we simply write phenol. Let's write the skeletal line structures for these compounds. So first compound is methylbenzene and second compound is 2-methylphenol. So when we write the structures, you will see the similarity between these two compounds. So let's first write methylbenzene. So the parent aromatic hydrocarbon in methylbenzene is benzene. So this is benzene, and methyl is the alkyl substituent. We can write it at any place because in case of a single substituent, it does not matter where it's connected to. That's always going to be the number 1 position. The second example is 2-methylphenol. So in this case, our parent aromatic hydrocarbon is a phenol, and phenol contains a OH group connected to benzene ring. So this is phenol. And when we have a phenol, the number 1 carbon is always assumed to be the one where OH group is connected or linked. So that would be number 1. Now we can either count clockwise or anti-clockwise because we need to find the position or the location of methyl functional group. So if we go clockwise, that would be 1, 2, 3, 4, 5, and 6. So in that case, methyl group is here. Okay, so this is the right answer. However, you may also choose to draw OH group at any other place. So for example, I can draw OH here. So that would be now number 1. And you can also go anti-clockwise. That's number 2, 3, 4, 5, 6. And then simply draw the methyl group at number 2 position. As long as your methyl group is at number 2 and OH at number 1, your answer is correct. These two molecules are same molecules. Only difference is that they are rotated at some angle, but they are same molecules.